All right. So this is the first lecture on particle image velocimetry. So the book that we are going to cover, and most of the examples are going to be from the book, and there will be some examples from our own reading. The book, Particle Image Velocimetry, Practical Guide by myself, third, and published by Springer. So the idea is that if you take, this is for example, a snapshot of the velocity field behind a wedge. And this is, for example, the unsteady velocity field and the flow is and or the vortices head around an aerofoil. So there are countless examples like this where we need to know, for example, here what is it head? Here also it is head, can be steady, it can be unsteady. So in all those cases, the flow can be sudden, it can be like impulsive, there can be many things. So all these things together, you see that this velocity field is therefore composed of so many transient structures, complexity. So, but you need to visualize the flow field, you need to see the flow field in entirety, and that is the prelude to particle image. So the principles of measuring velocity are quite simple. That if you want to measure, for example, the velocity of a flow, uh, such as a gas or pure liquids, but how to measure the flow? They do not contain moving objects that acts as a reference for you to track, identify the velocity, right? So it is not that easy. Therefore, how do? You use, for example, pressure probes. Pressure probes, as we already saw, it could be like your pitot tube. So it measures the different pressure and links it with velocity. Uh, and there can be like things like you can use the rotational wind anemometer, did not cover. And then it can also depend on the heat transfer. For example, a hot film or a hot wire anemometer is a perfect candidate for. In these cases, the velocity of the flow is finally derived from well-established relationship physics. For example, in the pressure probes, we use Bernoulli's. In the case of heat transfer, which is hot film or hot wire anemometry, we use what we called the heat transfer. So use that, the flow velocity is actually embedded with calculate. So we can kind of relate the two indirectly. So this is an indirect measurement, but these are very cheap. You can see, well, hot wire anemometry is not cheap, but pitot tube and rotational wind anemometry are very cheap. But hot wire anemometry is expensive because of its, it gives you quite a bit fast, high temperature. So, but in general, the indirect measurement techniques are easy to use, cheap to begin with. But their main advantage is because these are probes which are actually physically inserted into the flow field, they actually disturb the flow, the very flow that it is trying to measure. This leads to measurement errors, and they deliver also results at a single location. These are point-based measurements. In order to have an information about the whole velocity field, the probe needs to be traversed through the flow field. For example, you can never get an image like this. This is simultaneous, right? Here, you cannot get that information. You have to basically traverse the flow field, traverse the probe across the flow field. So, in order to obtain information about the velocity field, therefore, the probe needs to traverse across the flow field. So the process of traversing requires some time because everywhere you go, you spend some time taking the measurement and then you take time to move the probe to some other location. So therefore, this can only give you averaged data. It cannot give you unsteady flow information and definitely not snapshots that you saw over here. This kind of snapshots you cannot get in probe based. So this is the cannot get these probe based. right? Now you come to the next. Then what to do? You go for optical measurement. Now, optical measurements allow you to not intrude the flow. So basically, it can capture images, or it can even capture the data, which we saw in LDV or PDPA, by placing the sensors outside the flow field. So you are not really entering into the flow field. You are not, sticking something into the flow field. So in general, these techniques are very complex, and the instrumentation cost is high because of the accuracy. So these optical techniques or measurement techniques, which have found wider use, actually need tracer particles. Okay, so these tracer particles, we assume that they are going to follow the flow motion without disturbing the flow or the fluid properties. So by measuring the position of this tracer particles time, the velocity of the flow can be measured indirectly, because you are measuring the tracer particles velocity. You are not measuring the velocity of the flow, but the idea is that the tracer particles actually follow the flow field. So by measuring the tracer particles, you are measuring the velocity of the flow. And we are assuming that the tracer particles do not really disturb the flow field or the flow property. So these also come in different types. So one type we have already seen, that is the Doppler effect. It relates the speed of the moving tracer, the frequency shift of the light scattered, and that this is called LDV. It is a pointwise measurements. There are other variations like Doppler global velocity, which we did not cover. Okay, but you can understand that you can use the Doppler effect. You can use the frequency shift to measure the velocity, right? You can also use what we call the traveling time of the tracer particles between light barriers. This is called laser two focus or point measure. To measure, it's like you are basically doing a tracking. So at one light barrier, you have a tracer particle crossing. You see when it reaches the next time barrier, you divide the distance by the total time, get the point measurement. Of course, these light barriers are very close to each other. Then, of course, the thing that we are going to do over here is called the displacement of tracer particles in two instants of time. So this is called particle image velocimetry. It focuses on ensembles of tracer particles, not single tracer particles. Okay? But there are other variations which are called particle tracking velocimetry, focuses on single tracer particles. Okay? And these measurements can be both planar and volumetric and okay? There are also measurements which are called laser speckled velocimetry. So it basically tracks the displacement of tracer particles between two instants of time. It is usually between two laser flashes, right? And so this actually in PIV, remember, it is ensembles of tracer particles. Particle tracking velocimetry, it focuses on single tracer particles. So there is a difference between the two, right? So this is basically the principle of PIV. Look at this particular diagram in details. Expand this up a little, blow this up so that you can see that in this particular in this following, we basically state consists of several subsystems. Okay, now these subsystems are basically the seedings. Seeding is needed, as we call, these are basically tracer particles added to the flow. Then you have illumination. The tracer particles have to be illuminated in a plane or the volume of the flow at least twice with a known time interval between two. So like, for example, if this is the laser sheet, for example, it basically is passed through the fluidic system under consideration, and this is pulsed twice. Therefore, each laser sheet has got a time of the order of nanoseconds, and then you have a pulse separation. That means there is another laser sheet which comes of the order of microseconds or milliseconds even, okay, and illuminates the same location of the flow field, right? So This is the illumination. So it can be volumetric illumination also, as we will see in the case of micro PIV. But normally it is a pulsed laser. It is converted into a light sheet. You already know how to make. We use a mirror to direct the light sheet into the flow field, and there is a flow which contains now the tracer particles. These particles are therefore illuminated, and so they scatter. We already know a little bit of what scattering is. Then you have an imaging optics, which basically monitors the image and basically at 2 time. So the first light pulse is at t naught, the second light pulse is at t naught plus delta t. So you can actually see how much the particles have moved in between the laser pulses. And this will enable you to calculate velocity. So the recording is basically light scattered by the tracer particles has to be either recorded on two separate frames or on a sequence of frames camera. So the calibration, in order to determine the relation between the particle image displacement and the tracer particle displacement, calibration are required. Determine the relation. So usually you have a calibration target. And the evaluation, the displacement of the particle images between the laser pulses has determined evaluation of the PIV recording. And then we typically do a lot of post-processing to detect and remove invalid measurements, to extract complex flow quantities. For example, other shear, for example, wall shear, a lot of things we can calculate. So you essentially get images of the particles in the flow field, and by looking at the displacement of this image over a known time interval delta t, this is component wind tunnel, you should be able to see what the flow velocity is. Okay, so this is the very basic setup. It uses a laser and a camera system. You can use camera system also. So this is in general, in a nutshell, what here. Okay, so the second is that the principle of particle image velocimetry is that the tracer particles are added to the flow at a location where the flow of interest will not be disturbed. This is the first, important statement already said. So the flow cannot be disturbed. A plane of interest within the flow is illuminated twice by means of a laser light sheet gain. Then there is a time delay between the two pulses, and that must be chosen with respect to the flow velocity and with respect to the magnification. Higher the flow velocity, lower is the time delay between the two pulses. Okay? And it also depends on the magnification imaging. For simplicity, it is assumed that the tracer particles move with a local flow velocity between the two illuminations. So it moves between these two pulses are so close to each other that it moves with the local flow velocity. That is what the consideration is. And the light scattered by tracer particles is recorded by a high quality lens on two separate frames, a dedicated cross correlation digital camera. The output of the digital sensor is transferred to the memory of a computer. Okay, so this is not equal to 0, this is T1, and this is T. This is one of pulse. Okay, you can see that the images move to the particles may have a little bit with respect to each other. You can see this very clearly, and this is what is used for the cross correlation. Okay, now for the evaluation, the digital PIV recording is divided into sub areas, which we call interrogation areas. These are these blocks that you see. Okay, these are called interrogation areas. The local displacement vector for the images of the tracer particles of the first and the second illumination is determined for each interrogation methods. We will see what that is. It is called cross correlation. The local displacement vector of the tracer particles of the first and the second illumination, these are 12 pulses, right, is determined for each interrogation. For each of this interrogation area, we have to determine this. So it is divided into small sub areas. So this particular image whole image is divided into small sub areas, which you see, right? Okay. The evaluation is therefore repeated for all interrogations. Now, we can use high-speed recording with dedicated sensors. This allows for acquisition in kilohertz range. So that means you can actually now measure a very high-speed flow. In general, more complex PIV setups, such as video PIV, even tomographic PIV, adds a second and a third camera viewing at different angles. So all of these done. Tomography we already saw a little bit in your Schillerin POS. So non-intrusive velocity measurement, in contrast to techniques for the measurement of flow velocity employing probes, such as pressure tubes or hot wires, the PIV technique is an optical technique. Therefore, it depends on scattering of light. It is not a spectroscopic technique, by the way. There is no energy transition involved. Okay? So this allows the application of PIV even in high-speed flow, shocks, laminar boundary layers, very close to the wall, where the flow can actually be very sensitive to the presence of probes, especially in the case of shocks, because the shock is such a small zone. In order to actually determine the location of the shock, you cannot put probes right there, because those can actually severely compromise the flow field. So it is a non-intrusive velocity measurement. There lies the beauty of it. So PIV is a whole field technique, therefore, right? It is a technique which allows you to record images of large parts of the flow field in gas or liquid medium, and you can extract the velocity component out of these images. So this feature is the PIV technique. Now, the spatial resolution of the PIV is large, as you know, because it is taking a large whole field, and it depends on the resolution of your camera and optics to determine what kind of spatial resolution. Temporal resolution, which is the recording rate, is limited sometimes, unlike LTV or PTPA, which can be very, very fast. But 100 kilohertz PIV is so we are getting there. The PIV allows the detection of spatial structures even in unsteady flow fields. But the temporal resolution part is also important, because if it's a very rapidly moving flow field, then if the PIV framing rate cannot match, so therefore there will be a problem. In those cases, we'll rely on phase averaging, mode locking, and all those kinds. So the other part is the distribution of tracer particles in the flow field. Now, at qualitative flow visualization, certain areas of the flow can be made visible by, for example, putting smoke and dye. This is like, if somebody has seen this Reynolds experiment, you can see there is a dye injected which then wiggles, right? You can also insert smoke. You can see this very nice vertical structures, etc. And but that structure and the temporal evolutions can be studied by qualitative flow visualization. So you do not really know the magnitude. You do not really know the directions and the nuances, but it gives you an idea of what the flow field should look like. And therefore, this can form a prelude to the actual measurement. Now, for PIV, the situation is very different. You need a homogeneous distribution of the CD density, okay, for high quality PIV recordings. In a high quality PIV recording, from looking at these raw images, for example, at the lower side, on the lower bottom, see any flow structure. You cannot see structures that can be detected. It was only after processing that you be able to detect this. So because it's a homogeneous distribution of the medium, it does not really preferentially show any structures that you qualitative imaging parodying. So now comes the density of the tracer particles. So there are three densities over here. This is the particles are clearly visible. They are distinguishable almost. Here the particle is medium density. Okay? So you cannot really, it's a very hard onerous task to basically track these individual particles. Here the particle numbers are so large that their images overlap and you get the speckles. So basically you can see that when the particle density is really low, this particle tracking velocimetry, you basically track each particle. and you can calculate. It's more like a Lagrangian way of detecting the particles. Particle image velocimetry is of course medium density. So you can see this is medium. So it is kind of, it's very hard to find out individual particles and track them. So we use the interrogation windows that we talked about, sub areas within this image, and then we used ensembles. Then we use statistical means like cross correlation, find out the displacement. And here, of course, you have speckles. This is very large density. The lights actually overlap with each other, so you get speckles. And this is therefore called laser speckle velocimetry. Okay, so all of them adds a tracer particle, and all of them, you measure the scattering of the particles coming out. It's the density of the cedar that makes all the difference. Now, the other thing is that when you employ tracer particles for the flow velocity, we need to check for each experiment whether these particles will faithfully follow the flow field or not. Otherwise, the purpose is defeated, because if the particles do not follow the flow field, you are measuring the velocity of the particles and not the flow. In case of weak and strong velocity gradients, when there is very weak velocity gradient, strong velocity, okay, in the same observational field, you have to have a compromise. That means you can opt for a larger observation window. It requires bigger tracer particles because you have to get the light. Bigger the particles scattering, going to use the same light source, and it does not allow you to sometimes resolve the velocity close to the area where there is a very strong velocity gradient. Okay, because bigger particles may not be able to follow the. If you are observing a large observation window. Now, for illumination, for applications in gas flows, a high power light source for illumination of the tiny particles required, because high power means a lot of scattering. As a result of that, you will increase visibility of the particle essentially, and you also have to expose a video sensor or camera sensor. In principle, there is a need to use larger particles because of their better scattering, but this is in contradiction to the demand to have small particles because they have to follow the flow field. As we know, smaller the particles, this is intuition, smaller particles should be able to follow the flow field faithfully. Now, in most applications, you need to arrive at a compromise. Okay? So the compromise is one criteria for selecting light source for PIV is that they must allow to illuminate the observation area homogeneously, easier said than done, which means the profile of the beam will be expanded into a light sheet. It will be Gaussian or a top hat profile as closely as possible without any holes or gaps. So we already know what Gaussian beams are, so you need very high quality lasers. And the ambient conditions are also important in the sense that the optical setups needs to be robust against ambient conditions, noise, vibrations, background illumination. All these things are important, because if the setup, for example, is vibrating, how do you do? Because everything, the image quality will be pretty bad. Sometimes you mount everything on these optical cables, breadboards, even stages to minimize. Then, of course, the duration of the illumination pulse. Now, if the duration of the light pulse must be short because you want to freeze. This is like a stroboscopic effect. That means when in the theaters, if you see this, stroboscopes, which freezes. So you see the camera in this case, and your eye is like the camera, sees that the particles are frozen, right? So that means they not really move during the pulse exposure. If they do move, you will get blurring or streaks. Okay, so in this case, for example, you get streaks. In this case, you get well separated particles. So you need this rather than this. Okay, so the duration of the illumination pulse is very important. That means short enough to freeze the motion, okay, and have no streaks. Then, of course, the time delay between the two pulses is important, because this must be long enough to detect the displacement between the images of the tracer particles, with sufficient resolution, short enough to avoid too many particles to go out of field. Okay, because the particles are continuously moving. So it should be very short. If this is a high velocity event, then you have to make the time delay very short, because there can be off the plane components where the particles can go out of plane, or it might go out of the interrogation window and stuff like that. So the time delay between the illumination pulses must be long enough to determine the displacement, but it should not be so short that the particles do not really move also. So you need to have an a priori knowledge of the flow velocity or the kind of velocities that you are actually dealing with. Okay. So repetition rate is another thing. For standard PIV, we use double pulse Nd:YAG lasers with 2 oscillators. The time delay can be very short, of the order of microseconds. Consecutive PIV recordings can be done, but you generally get it in 10 to 20 hertz. But however, high-speed lasers allow recording up to 100 kilohertz. These are mostly associated with loss in pulse energy, resulting in very small observation areas. So you cannot observe large areas because the laser power will not be there. It will distribute it because you are making a sheet, so you're basically distributing the power everywhere. However, depending on the time scale of the flow phenomena, such systems may allow temporarily resolved measurement. I think a big thing, because you sometimes need to resolve the flow physics at very high temporal